This tutorial will show how to generate a time history plot. In this case, the excitation of the structure will be due to a person walking across this one bay concrete slab, which is 9 meters by 9 meters. We wish to obtain a plot of the vertical accelerations at the middle of the slab to make sure that the maximum acceleration is below so-called perceptible levels. In this model, we are attempting to model the dynamic effects of a person that weighs approximately 734 newtons, or 165 pounds, walking across the middle of the slab. We will assume that the person walks with a frequency of 2 Hertz, which means that a footfall impacts the slab every half second. We will assume that their forward speed is 1.5 meters per second, which results in a stride length of 3/4 of a meter. We will assume that the peak load will be 1.4 times their weight, or approximately 1 kilonewton, and that the duration of impact is 0.45 seconds. Thus, we will apply a pulse load of 1 kilonewton lasting 0.45 seconds, spaced 3/4 of a meter apart every half second. On the plan view, the path of the walk is defined with a line through the middle of the slab. Nodes have been added at every 0.75 meters, which corresponds to the stride length. The first step in creating our loading is to define a time history function for the footfall. We will add a new user-defined function and we'll call this function footfall. At time 0, the value will be 0. At 0.225 seconds, the value will be at the maximum, a nominal value of 1. And at 0.45 seconds, the value will be back to 0. This is our footfall pulse. To simplify matters, we will remove the other 2 program-defined functions as they are not needed. Now we will define a separate load pattern for each footstep. We will have a total of 11 footsteps. Now we will assign the footfall loads to the different joints that define the path of the walk. Selecting the first joint, we select Load Pattern Step 1 and assign a load of 1.4 times 0.734 kilonewtons in the negative z direction, and then hit Enter. This results in a load that is very close to 1, so for simplicity's sake, we will simply use a 1 kilonewton load. Click Apply to add the load. With the form still open, select the second joint in the path, and then switch to Step 2 and apply a negative 1 kilonewton load. Repeat this process for the third joint, and the remainder of the joints until you have assigned the joint loads for all 11 footsteps. Making the 3D view active, we can display the loads just applied as they walk across the slab. Now we will define the time history case that will apply the load patterns as pulses moving across the slab. We will name the new case walking. It will have a type of time history with a subtype of linear modal. In the loads applied area, we will apply the step 1 load pattern using our triangular function footfall. Next, we will add the step 2 pattern and so on until we have added in all 11 steps. However, we need to apply each of these footsteps at a different time as the person walks across the slab. To do this, we check the Advanced box and scroll over to the Arrival Time column. The first footstep arrives at time 0, and each step thereafter is incremented by half a second. The last step occurs 5 seconds after the first. Under the Other Parameters area, we will set the number of output time steps equal to 200 with a time step of 0.045. This gives a total output time of 9 seconds, or 4 seconds after the start of the last footstep. The last thing to set on the form is the modal damping. For this analysis, we will use 3%. Modal damping may have a significant effect on the time history response, so it is important to be as realistic as possible when setting the damping. Running multiple analyses with bounding minimum and maximum damping values may be appropriate. Next, we will review the mass source. For this analysis, since the time history input is not a lateral earthquake, but rather a vertical excitation, we will uncheck the Include Lateral Mass Only checkbox. We will also review the modal case. For this analysis, we will use 20 modes. The last thing we will do before running the analysis is to set the active degrees of freedom. We wish to limit the analysis to the vertical degrees of freedom, so we uncheck the UX, UY, and RZ checkboxes. We can now run the analysis. With the 3D view active, we can display the deformed shape for the walking load case. For the first time step, we can see that the first footfall load is applied. At nearly 5.5 seconds, we can see that the footfall is now at the far side of the slab. The information we want from this analysis is a plot of the vertical acceleration at the midpoint of the slab, which is joint 16. To plot out the acceleration, we go to the Display Plot Functions command. The default plot generated is base shear, which is not what we want. We will alter this by going to the Define Plot Functions button and clicking the Delete button. Next, we click the Add button and select Joint Acceleration. We will change the name to Joint 16 Acceleration. Select Joint 16 from the Joint Label drop-down list. And select the UZ component. A plot of the vertical acceleration in millimeters per second squared is displayed for joint 16. The maximum acceleration is 14.7 millimeters per second squared, which is approximately 0.15% g. The typical accepted standard for office buildings is that acceleration should be below 0.5% g, so that it will not be noticeably perceptible. So our slab is okay. Note that the peak acceleration occurs at the midpoint of the walk, as we would expect due to the fact that joint 16 is at the midpoint of the slab. Now let's look at the vertical acceleration for joint 21. Which is at the far end of the loading path. Clicking the Define Plot Functions button, we click the Create Copy button. Renaming our copy we select joint 21 and change the color. Now we switch the vertical function and we see that the peak response for this joint occurs at the end of the walk as expected. We can also plot both functions simultaneously and adjust the time range of the plot. We can easily view the tabular data for the graphs by simply clicking the Tables button and the image may be captured and printed. The plot parameters may be toggled on and off. We can also save the plot to the Model Explorer tree for easy recall. This plot has been saved under named plots. As a last check, we will alter the modal damping. We will change the damping to a very low value. Let's say 0.5%. After rerunning the analysis, we will view our time history plots. And although the vertical acceleration has increased to nearly 20 millimeters per second squared, or 0.2% of g, it is still below our target threshold of 0.5% g, so it is okay. Although we have focused on acceleration response for this study, velocities and displacements, along with other quantities, may also be plotted. Here we will plot the vertical displacement at joint 16. This concludes this tutorial on the plotting of time history data.